Hello, my name is Juan Luis, and I'm going to present Forget About the LiDAR, Self-Supervised Depth Estimators with Met Probability Volumes by Juan Luis Gonzalez and Moonshot Kim from the Big Lab at Korea Advanced Institute of Science and Technology. First, I would like to thank the LatinX in AI community to let me present my NeurIPS 2020 paper in this workshop. We propose to forget about the LiDAR for the supervised training of single image depth estimators and show that our self-supervised method achieves superior performance than state-of-the-art self, semi, and fully supervised methods on a challenging Kitty dataset. Here we show an input image, the generated depth map, and an animated texturized point cloud. As you can see, our method generates very good depth estimates for thin objects, faraway objects, and textureless objects like the ground and the sky. Our main contributions are in a novel mirror occlusion module, which we call MOM, which is a multi-view occlusion mask generator. The computed masks are very realistic and are used to filter the invalid image regions to parallax for two views with known or estimated camera positions. We also propose a new two-stage strategy. First, we train our network, which we call FalNet, for plane stereoscopic view synthesis by penalizing the synthetic right view in all image regions. Secondly, we train our FalNet for single image depth estimation with our MOM to remove the burden of learning the synthesis of right occluded contents and provide self-supervision for the left occluded regions, which are ignored in the reconstruction losses. Lastly, we shed light on the effectiveness of the mirror exponential disparity representations, which we call MET, for self-supervised single image depth estimation. This small change from the linear to the exponential domain makes our FalNet, even without MOM, perform surprisingly well compared to the recent state-of-the-art methods. Figure B shows our network trained with only one training stage without our MOM. And as you can see, there are many artifacts around the objects, and the depth estimates are not smooth enough. Figure C shows our FalNet after the second stage of training. That is, this FalNet has been fine-tuned with our MOM. And as you can see, all the artifacts have been removed, and we get very sharp depth estimates. Our network architecture is simple yet effective. We call it FalNet, and it is an autoencoder network that incorporates a MET representation in its output layer. Our FalNet maps a single left view input to an n-channel disparity logic volume. These disparity logics can be channel-wise softmaxed to form the mirror exponential disparity probability volume, which can be quantized and sum-reduced to give rise to the final predicted depth map. Our disparity logics can also be progressively shifted to the right camera and softmaxed to give rise to the right from left MET probability volume. The element-wise multiplication of this probability volume with equally warped versions of the input image, followed by a sum reduction operation, produces a synthetic right view, which we use to train our network for the stereoscopic view synthesis in a self-supervised manner. Exponential quantization. We observe significant improvements by adopting exponential disparity quantization, which is reasonable, as linear quantization of disparity assigns most sampling positions to the very close by objects due to the inverse relation between disparity and depth. In figure A, we can see that disparity quantization, in effect, assigns most sampling positions to the very close by objects. You can see most sampling or quantization positions or levels have been assigned between 0 and 20 meters. However, using exponential disparity quantization, we get a more evenly distributed quantization scheme. We can compare linear quantized disparity in the figure B and our exponential disparity quantization in figure D. As you can see, using linear quantization of disparity is very bad for the faraway objects, and also it does not produce a very smooth estimate in comparison with figures D, C, and E, which use exponential quantization of disparity. Our mirror occlusion module. Our mirror occlusion module, or MOM, is a multi-view occlusion mask generator module that allows our FalNet to directly learn single image depth estimation by cross-computing occlusion maps from the met probability distributions of two training images with known or estimated camera positions. For more mathematical details, you can refer to our paper. We propose a two-stage training strategy in which, in the first training stage, we train our FileNet for view synthesis with L1, perceptual, and smoothness losses, and keep a fixed copy of the trained model. In the second stage, enabled by our MOM, we fine-tune our FileNet for inverse depth estimation with an occlusion-free reconstruction loss, and a smoothness loss, and our new proposed mirror loss, which computes the error between the actual disparity estimate and the flipped input disparity estimate from the fixed copy of the network. And this is weighted by the occlusions in the left view. So in this way, we can supervise the left occluded contents that are always not taken into account in the reconstruction losses. Our qualitative results. Our depth estimates are more detailed and more consistent than the previous methods. As you can see, our depth estimates are much sharper on pedestrians, traffic lights, sky regions, bikers, street lights, and trees. Quantitative results. Our method outperforms the most recent methods by a considerable margin. We evaluated our method on the improved Kitty eigentest split, and we obtained the state-of-the-art results. We outperformed previous methods with a very large margin, particularly in RMSE and A1 accuracy. Note that even our method, without any post-processing, already outperforms all previous methods in most metrics. Ablation studies. We present extensive ablation studies that show the effectiveness of our proposed MET and MOM. First, we ablate our FileNet with linear quantization, and we observe very poor performance. Next, we ablate the number of parameters, and we observe that with 17 million of parameters, our FileNet gets to its best performance. Later, we ablate the number of quantization levels. We observe 49 quantitation levels to be better, so we stick to 49 quantitation levels for our best model. Next, we evaluate the training dataset with Kitty and cityscapes, pre-training on cityscapes and then retraining on Kitty, and also training with Kitty and cityscapes simultaneously. We observe better performance with training with Kitty and cityscapes simultaneously. We also train with additional 20 epochs to show that our improvements do not come from additional epoch, but they come from the fine-tuning with MOM, with our mirror occlusion module. We also ablated fine-tuning or retraining from scratch with the MOM, and we saw similar performance improvements, but with the additional training epochs. And finally, we fine-tune all the network variants with our MOM and observe consistent performance gains. More results and ablation studies are presented in our paper and supplementary materials. You will also find these texturized animated point clouds, which shows how consistent are our depth estimates, and as they can reveal the 3D geometries of the scene. In conclusion, we show that a state-of-the-art single image depth estimation can be achieved by light and straightforward autoencoder networks that incorporate MET in representations in their output layers, and that our two-stage training strategy with our mirror occlusion module aids in learning precise depth instead of plain view synthesis. Our method outperforms the Dorn supervised baseline by a large margin in most metrics, which suggests that we can forget about the LiDAR for the supervision of single image depth estimation networks. Any task that requires handling of occluded regions caused by rigid motions, such as learning stereo disparity, single image depth estimation from monocular videos, and optical flow can benefit from our MOM. Thank you, and here we present our contact points.